My dear students, today we are going to talk about K epsilon model. Okay, we are going to talk about K epsilon model. Okay, now my dear students, K epsilon model for turbulence is one of the most kind of turbulent model and very important to equation model to simulate the mean flow characteristics for turbulent flow conditions. Okay, now basically all, as you know, that all these models are the basis of Renault average Navier-Stokes family, and these turbulent models where all the effect of turbulence are modeled, means that the level of a turbulency in that particular fluid flow region or in that particular fluid flow domain will be captured by these different types of turbulence model. Okay, so as you know that this is a kind of a two equation model, this is a kind of a two equation model, and means that as you know that as in Renault's average Navier-Stokes equations, or because these model are the basis of that, we have different conservation equations or conservation laws are available on the which we are going to solve it. Okay, and add what are the differences in different conservation equations and these models is that these models also solve two different variable transport variables. You can say that two, we can say that additional two additional transport variables are available. Two different transport variables are available. Who are those two transport variables? One is your K and another is epsilon, means that one is K, turbulent kinetic energy, and the epsilon is that dissipation rate, means that it is basically K is the turbulence kinetic energy, the kinetic energy available in that particular turbulent flow, and epsilon is the rate of dissipation, means that it is a measure of the rate of dissipation of turbulent kinetic energy in that particular flow field or fluid region. Okay, now basically my dear students, this model is shown to be reliable for free shear flows, and such that the ones with relatively small pressure gradient but might not be the best model for the problems involving adverse pressure gradients or large separations and complex flow with strong curvatures. So my dear students, the lower level of a turbulency in any fluid flow region, we can say that we can capture this particular by using this particular model, or by using this particular equation we can solve. But where the huge amount of adverse pressure gradient is available, where the complexity is flow in any fluid flow region is more, so for that purpose we have other turbulent models are available on the basis of which we can solve that particular problem. Okay, so basically there are different categorizations. You can see that different variations of K epsilon models are available, and the one is standard K epsilon model, second is your realizable, third one is your RNG. Okay, standard, realizable, and RNG. These three are different types of standard K epsilon model, realizable K epsilon model, and RNG K epsilon model. These three different types of turbulence models are available to solve our problem. Okay, now we will move to our the mathematical part of this particular equations. So my dear students, we have two transport equations in the terms of PDs, partial differential equations, to solve the fluid domain, and in the form of turbulent kinetic energy and in the form of dissipation rate. So we can write these two transport equations, transport equations, the transport equations for K and epsilon. For K it will be del K upon del T plus ui into del K upon del xi equals to del upon del xi into Vt upon sigma k del K upon del xi plus Vt into del ui upon del xj plus del uj upon del xj into del ui upon del xj minus epsilon. So one, this will be the one equations, and another equations for this it will be, another equation for this it will be like this: del epsilon upon del t plus ui del epsilon upon del x j equals to del upon del xj into Vt upon sigma epsilon del epsilon upon del xj plus C1 epsilon upon k p minus C2 epsilon square upon k. So this will be another equation. One equation is this, one transport equation is this. These two equations comes from, these two equations, my dear students, comes from the earlier Reynolds average based Navier-Stokes equations, where we added two transport variables. One is turbulent kinetic energy and second is your turbulent dissipation rate in your different the conservation equations, which is basically a conclusion of conservation of mass, momentum and energy. Okay, now in this particular equation you can see a denotation like p. So this p is the generation of k, and this, the value of this particular p, the value of this particular p will be equals to Vt into del ui upon del xj plus del uj upon del xj into del ui upon del xj. So this is p. P is the generation of Ka, and the value of this p is can be finding, we can find by Vt into del ui upon del xj plus del uj upon del xj into del ui upon del xj. Okay. Now this particular term, this Vt is known as nothing but this nu t. This nu t is nothing but the turbulent viscosity. Okay, turbulent viscosity means that the viscosity available in that particular turbulent flow, in that particular fluid flow region, that is denoted by turbulent viscosity. Okay, now how we can calculate the value of that particular Vt? You can see here that the value of Vt we can find here. Now we will see that, now we can see that the value of Vt, the value of nu t, the value of nu t, which is you can see that this nu t is your turbulent viscosity. Okay, and the value of this nu t turbulent viscosity is calculated with the help of a formula, which is nu t equals to C mu k square upon epsilon. So my dear students, from this particular equation nu t equals to C mu k square upon epsilon, you can find the value of turbulent viscosity which is available in that particular turbulent flow. And the other variables like C mu, C1 epsilon, C2 epsilon, sigma k and sigma epsilon, these are the different types of constants, and we have the value of C mu. Value of C mu will be equals to 0.09. Value of C1 epsilon will be equals to 1.44. Value of C2 epsilon will be equals to 1.92, and value of sigma k will be 1, and value of sigma epsilon will be 1.3. So these are the different types of constant empirical values we have here. We can directly put it these values, and while performing our computational fluid dynamics analysis, my dear students, we can, these values are automatically in our CFD platforms, and we can take these values to compute our fluid domain. Okay, now, so my dear students, after that, the momentum equations or the thermal energies or the conservation equations can be written in this particular format. So how it is possible to compute it? Why? As we can see that we have, how we can solve that particular conservation equation. So we can write it as del T upon del T plus ui del T upon del x j equals to del upon del x j into alpha del T upon del x j plus s. So my dear students, basically you can say that the conservation equations in a final form we can write as del T upon del T plus ui del T upon del x uj del T upon del xj equals to del upon del xj into alpha del T upon del xj plus s. Okay, where T is the temperature and is the source term which is Renault decomposition. Okay, and as you know, this T is your temperature. Okay, means that the thermal part, the thermal energy exists in that particular temperature, in that particular fluid flow. We are going to consider the temperature. Okay, now as you know that we will remind if the Renault decomposition. So the Renault decomposition, what it says that we are decomposing it, saying what we are doing, basically we are decomposing the velocity component with respect to time in that particular fluid flow. Okay, means that u j will be equals to capital U j plus small u j. Okay, the mean velocity plus the fluctuating velocity. Same in similar manner, T will be equals to your T bar plus T dash. Okay, this is how we are going to decompose our velocity component and the temperature component. This is the velocity component and this is the temperature. Okay, this is how we are going to decompose. Okay, now after putting these values into the above equation, we will find it after putting these values we will find it del T bar upon del T. Put these values in this particular equation. Put these values in the del T bar upon del T plus u j del T bar upon del x j will be equals to del upon del x j into alpha del T bar upon del x j minus u I dash T dash plus s. Okay, so this is the final equations we will achieve here. You can see that how del T, after putting the value of uj and T in this particular, we will have del T bar upon del T plus ug del T bar upon del xj equals to del upon del xj into alpha del T bar upon del xj minus ui T dash bar plus s. S is a source term from Renault decomposition. Okay, now this alpha T is the turbulent diffusivity. This alpha T is your turbulent diffusivity in the flow. The alpha T is turbulent diffusivity in the flow. The value of alpha T is a turbulent diffusivity, and the value of alpha T you can find from nu T upon sigma T. The turbulent diffusivity you can calculate from here, alpha T equals to nu T upon sigma T, and where the sigma T is turbulent Prandtl. Okay, this is the turbulent diffusivity, and the value we will get from nu T upon sigma T. Nu T is your turbulent turbulent viscosity, nu T is your turbulent viscosity available in turbulent flow, and the sigma T is your turbulent Prandtl or the turbulent Prandtl number. Okay, So from here we can calculate these values, and we will do and to calculate our the value of alpha t, nu t, sigma t, and all these things. Okay. So my dear students, you can calculate these values of alpha t and sigma t from these particular equations. And my dear students, different studies and different research shows that the value of sigma t, means that the value of this turbulent Prandtl number which exists in that particular flow varies a little bit across the flow. Okay, means that depending upon the nature of the flow, depending upon the flow to flow regime, the value of this sigma t varies. And this, the variations from one flow to another flow, one flow regime to another flow regime, is quite small. Okay, therefore the value of this particular sigma t, therefore the value of this particular sigma t we can take is as a constant in different we can take is a constant. Okay, if the variation is quite small in different flow regime, so we can take the value, this particular value as a constant in our calculations. Okay, and if we talk about the flow of air, a value of 0.9 may be taken. If we are talking about for the flow, the air we are taking as a fluid, and we are going to study the behavior of that particular fluid air, so we can take the value of sigma t, the turbulent Prandtl number, is equals to 0.9 approximate in that particular fluid flow region. And okay, and it should be pointed out that the buoyancy and streamline curvature affect as sigma t, the value of sigma t. Okay, so my dear students, that's how we can have the turbulent equation, which is a two equation model, which is a k epsilon model in our turbulent flow. Okay, how we can do it, and for again, the if I talk about the application purpose of this particular, okay, so this particular equations can be used for different types of small level of a turbulency, or the where the turbulent level is not too complicated, the flow nature is not too complicated, or too much variations is not available in that flow regime. So where there we can use this particular turbulent model to solve our turbulent problem in computational fluid dynamics. Okay, hope you understand it, and please just go through it and try to do at your home. Okay, thank you so much.